this chapter, we're going to look at topics related to measurement. In this lesson, we're going to look at rates and ratios.
Okay, everybody. So in this lesson, we're going to compare rates and ratios. So a ratio is a comparison of one number to another with the same units. Okay, there's the trick right there. It's the same units. Now, you can express a ratio in a couple of different ways. You can use this method right here, A colon B, A to B, which is equivalent to the ratio written like this in fractional form, A over B. Okay. So now we're just going to take a look at a quick example, and then we'll do some other examples together in just a moment here. So just to illustrate this, consider the following. So two friends, Rachel and Sarah, decide to keep track of how many texts they sent per day for 3 days. Okay, and their findings are stated below. So here's Rachel, Monday, Tuesday, Wednesday, 46, 38, 81. And then Sarah, we've got Monday, Tuesday, Wednesday, 23, 40, and 54. So write the ratio in reduced form of the number of texts Rachel sent on Wednesday to the number of texts Sarah sent on Wednesday in both those forms. Okay, so we're looking at Wednesday, and it's going to be, what is it? Sorry, Rachel. Yeah, I'm sorry, Rachel to Sarah. I just lost track of who was supposed to come first. So it's supposed to be 81 to 54, or 81 over 54. Now, both of those, though, in both of these forms can be reduced in a very similar way. Both these numbers are divisible by 9. So we can actually remove the factors of 9 from there. So these are going to become, if I divide 81 by 9, I get 9. And 54 divided by 9 is 6. And then so the same thing happens over here. You're going to get 9 to 6. Now, that actually can be reduced even further, because both of those have a factor of 3 to them. So I could write this actually as 3, if I divide that out of both, 3 to 2, which is going to be the same as 3 over 2. Okay, so we've got these two different forms here, but they can be reduced in basically the same way. It's just a matter of how you write them. Then it says, write the ratio in reduced form of the number of texts Sarah sent on Wednesday to the number of texts Rachel sent on Wednesday in both forms, A to B and then A over B. So in this case here, all we're asking you to do is to flip these numbers, and so it becomes 54 to 81, which is also 54 over 81. But you can guess how we're going to go about doing this, and so eventually we're going to get 3 to 2, which is going to be the same as, oh, shoot, not 3 to 2. I immediately looked over there, and then I just grabbed them in the order that I saw them. I wasn't thinking about that. This is going to be 2 to 3, or 2 over 3. Now, compare that with a rate. A rate is a comparison of two quantities where the units differ, okay? Two different units. So, I mean, a classic example of a rate would be speed. Speed is, meters per second. We're comparing two different units, or quantities with two different units there. So just as an example here, Rachel sent 165 texts in 3 days. So express the total number of texts Sarah sent over the 3 days as a rate. Well, so what we've got here is 165 texts over 3 days. Okay, well, 165 over 3, what we can do there is simply reduce that. This is the same as 55 texts per day, which gives you a sense of how fast she's texting. Now, inadvertently, what I did was create a unit rate. A unit rate is a base rate. It has a denominator of 1. So that's basically what I just did up here. Okay, so here's a rate. These are both rates, but this one right here, this is a unit rate because it's per one of something. Okay, so for example, 25 meters per 2 seconds is the same as 12.5 meters per 1 second. So when it asks here, what is the unit rate of Sarah's texts? Okay, that's what we've just figured out, is 55 texts per day. So that sort of thing makes it easy to kind of extrapolate beyond this. If she continues to text at the same rate, how many texts would she send in 1 month or 30 days? Well, we know that she sends 55 texts per day. This is almost like a conversion. What I want to do is get rid of those days there. I'm going to multiply this by 30 days. The days will cancel, and I'm going to be left with a number here that's going to be the number of texts. And that's just going to be 55 times 30. I'll just do that over here in my calculator. That's Actually, I just realized that that 137, the page number, is a little bit confusing here. This will be 1650 text, 1,650 texts. Okay, so now we can use proportional reasoning, unit analysis, or unit rate to solve rate problems. And so that's what we're going to take a look at. We're going to look at a rate problem right here. So what does it say? It says Tommy purchases 3 bottles of water for $4.95 after paying. Okay, he realizes he's having friends over tonight, so he goes back and buys 4 more bottles of water. Determine how much he paid in total for the 7 bottles he's using. Okay, so one way of doing this is to set up proportional reasoning. So we know that it's $4.95 per 3 bottles. So we want to compare that to or create an equivalent ratio there, but we don't know how much it's going to cost, but we do know it's 7 bottles here. So how do we handle that? Well, what we do is we cross multiply, and so you've done this before. So it's going to be 3 bottles times x. So 3x is going to equal 7 times 4.95. Now I'm going to do that on my calculator on the side here to make sure I get it right. So 34.65. And then I'm going to divide by that 3, okay, to get $11.55. And so that's how much he would pay for 7 bottles total. Or we could use unit analysis. So 7 bottles, and we're going to multiply by $4.95 for every 3 bottles. Now notice that the bottles cancel here, and so what we're left with is 7 multiplied by 4.95 over 3. Okay, and so I'll do this with my calculator. 7 times 4.95 divided by 3. Now, just so that you don't think that I'm doing something weird here, I'm going to show you what I did on my calculator. So that was my previous work here. So this is what I'm doing right now. When I press enter, I get 1155. Or we do unit rate. So 4.95 per 3 bottles here. So I'm going to just divide that 4.95 by 3 to get it's 165 per bottle. So now if it's 165 per bottle, and I want 7 bottles, I'm just going to multiply that out here. Oops. And so this is going to equal 165 times 7, and there it is again, $11.55. So there's a few different ways that we can go about reasoning this sort of problem through. Okay. Okay, this next question says, Brianna's chocolate chip cookie recipe will make about 3 dozen chocolate chip cookies. The recipe calls for 2 1/4 cups of flour and 3/8 cups of baking soda. Okay, so if Brianna was to adjust the recipe to include 1 cup of baking soda, how many cups of flour would she need to use? Okay, well, we're working with a couple of somewhat ugly numbers here. So I tell you what, that 2 1/4, just to start off with, this is how I prefer to do this. 2 1/4 is actually not as useful in many ways as the improper fraction version of this. So we're going to convert this to an improper fraction. 2 times 4 is 8, plus 1 is 9, so it's going to be 9/4. I think that's a little bit easier to work with. So right now, what we've got here, and we're not even worried about the number of cookies. I actually thought that the question was going to be more about the number of cookies. It's about the recipe here. So Brianna was to adjust the recipe to include 1 cup of baking soda. So what we're going from here is we've got 9/4 cups of flour, okay, and that's compared to 3/8. Okay, so this is flour, this is going to be baking soda. And I'm going to set this up as a proportion, because I think this probably sets itself up nicely for that, even though the numbers are kind of ugly. What's going to happen here is she wants a single cup of baking soda. The question is, how many cups of flour does that lead us with? Sorry, I should put cups of flour there. So we're going to cross multiply and divide here. So 1 times 9/4 is simply going to be 9/4. I love that. And then this becomes 3/8 multiplied by x. So in spite of the fact that I have a complex fraction here, which simply means fraction in a fraction, with the one step here, I kind of eliminate that. Now, it's still got fractions there, but so be it. So now what I'm going to do is I'm going to multiply both sides of the equation through by 8 to get rid of that denominator. And when you multiply 9/4 by 8, we'll do it over here. Okay, so it's going to be 8 times 9/4 is going to equal 3x, because that 3 stays there. 8 divided by that 4, because I can do this in whatever order I want here. 8 divided by 4 is 2, and 2 times 9 is going to be 18. And then I'm going to divide both sides by 3, and 18 divided by 3 is 6. So what that means is we're going to have to use 6 cups of flour. Okay. Now, I know you probably could have converted those to decimals and done that a little bit quicker on your calculator, but I want you to see what you can do with just fractions and the way their numbers are the way they're written. Okay, so the question says here, Paul hosted an annual wrap-up party for his hockey team last year. This year he's hosting the party again, and like last year, he will be serving prime rib roast. Awesome. Last year he bought 8 kilograms for $173.12. This year he bought the roast for $10.13 a pound. Note that 1 kilogram is equal to 2.2 pounds. So which year was more expensive? Well, okay, let's figure out what's going on here. So last year he bought 8 kilograms at $173.12. So what we want to do here is this year's price is given as dollars per pound. So what we want to do is we want to take this $173.12 per 8 kilograms. Okay, what we want to do is we want to first of all convert this to a unit rate, and then I want to convert that unit rate into a different. We want to convert it into pounds, not kilograms. So first of all, what I'm going to do is I'm going to divide that $173.12. Do that on my calculator. $173.12. I'm going to divide that by 8. And when I do that, I get $21.64 per 1 kilogram. Okay, so now I've got a unit rate and I've got a unit rate right here. So now what I want to do is I want to compare them. So I want to convert this $21.64 per 1 kilogram. Okay, what I'm going to do is I'm going to convert that, and I'm going to do that by using my unit conversion, my unit analysis. I'm going to multiply that by a conversion factor. I want the kilograms to go away. So I'm going to use this ratio up here. 1 kilogram is 2.2 pounds. I want pounds in the denominator, so 2.2 pounds. And when I do that, my kilograms are going to cancel. I'm going to get $21.64 over 2.2 pounds. Now, I know that I still have to work with that a little bit. I still got to convert that into a unit rate, but at least it's smaller numbers than I would have been working with otherwise. So 21.64 divided by 2.2, that is $9.84 per pound. Okay, so now let's compare these. This year, he spent $10.13 per pound. Last year, he spent $9.84 per pound. This year is more expensive. Which stands to reason. Prices go up. So now let's take a little bit more of a look at rates of change here. So the slope of the graph represents the rate of change, and we calculate it by doing the rise over the run. Okay, so this is the ratio of the change in the dependent variable, okay, the rate of change in the dependent variable y compared to the change in the independent variable x. And I like the fact that we're using that vocabulary there, right? Dependent variable on the y, independent variable on the x here. And it's the steepness of the graph that shows us how quickly or how slowly this change is happening. Okay, so the deeper the graph, the greater the slope, the greater the rate of change. In other words, if you've got a really steep graph, what that means is the y-coordinate is changing very, very quickly compared to a change in the values along the x-axis. Okay, now a positive slope indicates an increase. A negative slope indicates a decrease, right? So if the line goes like this, that means that as x increases, the y is increasing. But if it goes down like this, that means that the y is decreasing as x is increasing. Okay, and then you see what happens when you got a really steep line that goes in either direction, or a fairly shallow line there, okay, where it's a little bit flatter. Anyway, let's take a look at an example or two here to wrap this up. Okay, so let's take a look at this question here. It says, Dave entered his car in a long-distance car race, and he traveled the first 150 kilometers in 2 hours. Okay, and then after 6 hours, he had traveled 650 kilometers. So the first question here, or the thing that we need to do here, is plot the ordered pairs to represent the situation. Explain why 0, 0 is included. Okay, well, let's take a look at our grid here. So in this case here, in a situation like this, we know that distance, and this is going to be in kilometers, is going to be the dependent variable. It's going to depend on time. This is going to be in hours. Okay? So along here, I don't know, what do we got here? It's supposed to be up to 6 hours. Let's go 1, 2, 3, 4, 5. So if we go, 1, 2, 3, 4, 5, 6. Okay, we can get all that time in there. And then we'll go up in terms of 100 here. So 100, 200, 300, 400, 500, 600. You got to look at the scale carefully here. We know that at 1 hour, at 2 hours, he's gone 150. So that's going to be right here. Okay, and then after 6 hours, he had traveled 650 kilometers. So that's going to be right up there. Now we're going to include the 0, 0 there. And so explain why 0, 0 is, over here, explain why 0, 0 is included. Well, that's because if he has traveled for 0 hours, he has gone 0 kilometers. Okay? Now, notice that these are not connecting in a nice smooth line here. So let's take a look at this. It says calculate Dave's average speed between 2 hours and 6 hours. Is this a rate of change? Well, okay, first of all, I can even say yes it is, because as soon as we say average speed, well, speed is a rate of change, right? Now, the average distance there, okay, or the rate of change to the average speed is going to be the change in distance over the change in time. And so let's think about that. We went from 150 to 650 over, 6 minus 2 hours here. So 650 minus 150, that's going to be 400 over 4. So that's 100 kilometers per hour on average. And so that's really going to be the slope of that line segment. Okay? Every hour is going to go up 100 kilometers. And it says, without doing any calculations, how can we tell that the average speed in the first 2 hours was less than the average speed during the next 4 hours? Well, if I just connect those dots there, like that, well, I can tell visually, just by a quick visual inspection, that the slope of this line segment is not as steep as the slope of that line segment. So that's how we answer that. Okay, the slope of the segment covering the first 2 hours isn't as steep as the subsequent 4 hours. So that's how I know. Okay? Now, as a continuation of this problem, can keep going here, and it says, on the right is a graph that represents the amount of fuel left in Dave's tank compared to the distance he's traveled during a part of the race where he drove a constant speed. Okay, so constant speed, it's important here. Calculate the slope. Okay, well, the slope here, remember, is going to be y2 minus y1 over x2 minus x1. So we just have to decide which of these is going to be the first point, and I'll just say that, and this will be the second point. And so now y2 minus y1 over x2 minus x1. So negative 10 over 100. So this is negative 1/10. Now, of what though? How do the units work here? Well, on the y coordinates it's liters, and this is okay. Well, that's a weird thing to throw down there, d. But this is going to be liters per kilometer. So we're losing a tenth of a well, you can think of it like that. You're losing a tenth of a liter per kilometer. Okay, is one way to do it, or 1 liter per every 10 kilometers. So the amount of fuel, okay, the amount of fuel is, oh, I'm not sure exactly where they're going with this. Is the amount of fuel is first of all is the dependent variable. Okay, oh, it looks like I've jumped ahead here. So the rate of change is going to be negative 1/10 of a liter per kilometer. So the amount of fuel is decreasing at a rate of 1/10 of a liter per kilometer. Looks like there's just a few different ways of saying that here. Sorry, this one threw me off here. I wasn't expecting that. Anyway, so it's kind of going over the same ground a couple of times here, but I hope that makes sense.